All right, so do people still have the Brooder? Do people still have the Brooder file up, or if not, okay. If you don't have it up, you should remember that you want to start. So, for the Brooder data set, we were using the special version of Skyline that I created for this course, which is in your installers folder, Skyline Daily application files. And so you have to go to this Skyline Daily 4.1.1.18127, and then you just run the Skyline exe out of here, or the Skyline Daily exe out of here. So, and if you haven't already, it might be helpful to create. I just have I have a command prompt up with the name of that file in it. So you can just do that, like I'm in my documents folder and I type USB installers Skyline Daily 64-bit applicate, and I'm just using tab to expand here, and then type Skyline Daily and then exe. So that gives me a command that I can do at any time, so I don't have to go through the Explorer and find that exe. And then if I run that, now I get Skyline. So that's another way to get there fairly quickly, or you can just find this and double click it. So has everybody got that? And in theory, if you had closed it already, it should, when it comes up, I guess just to be with the people who have it closed, I'll do that. Now when I run it, it should come up with hands-on Brooder or Brooder, and we want Brooder. Hands-on Brooder is just going to be the template with no data imported into it, right? So we want the one that has the data imported into it. But actually, that's kind of long. So before we do that, I just want to make sure we do one more thing, just to make sure that we can all export the right method. Go up to where's it going to be? Where did I put it? Oh, right at the top. So at the top here, where you have DI intro, LFQB, and DI pub, there's an MS-stats annotations.sky file. And because this Skyline Daily is not the Skyline that you installed MS-stats into, I just want to make sure that everybody gets the right annotations. So go ahead and open this MS-stats annotations file. And that will go much quicker. And then if you now go and have a look at document settings, you'll see that we've got bioreplicate and condition. And if you look at the reports, you'll see that we have an MS-stats input plus report, which is a report that is MS-stats columns with a few extras. So does everybody have that? Yeah, don't go to the Explorer and double click it. You have to do you have to have this Skyline Daily open, and then click the open button, find this, and then open it. Because yeah, you installed Skyline, so now there's a file association in your. You're at the Explorer and you double click, it'll pop up the other version of Skyline. What we're trying to do is train this version of Skyline to know something about MS-stats. So that's one nice way to pass around annotations and reports, is to just associate them with some blank document like this, and then have everybody, your friends, open them, because Skyline will pick them up based on their presence in another document. Does everybody have that? Okay, so now let's go down to the file menu and open that Brooder, not hands-on Brooder, but the main Brooder document that has all the imported data in it. And now what we need to do while we're waiting for it to open, what we need to do is we're going to need to annotate the replicates. And we just, in the latest Skyline Daily, actually, well, I can't show it to you yet. I'll show it to you in a moment. In the latest Skyline Daily, it has the ability to import annotations, and we can do that at the command line. So I'm hopeful that actually by the next time I teach this, I'll be able to have a command line script that does everything and just leaves us with an MS Stats report that we could then use. But at this point, we have to do. I showed you that I could run an MS Stat. I could have the command line export a report and then run an R script on it. But I did that on the other computers. But the problem is that we still have a step where we need to annotate what we imported. So that at the time that I designed this, that wasn't possible. It's possible in here, and I haven't actually done the work to show it. So, but yeah, so we need to tell MS Stats what the condition and bioreplicate are for all of those files that we imported, right? So we can't actually use the command line to export this report because there's an extra step that wasn't possible to annotate until just very recently, or to automate until very recently. So okay, but if you go in here and you look at if we go in Documents, USB, and if you go into DIPub Bruderer, you can see that there is a files.csv. So double click to open that. And you could imagine that these could be fairly extensive sample annotations. In this case, all we have is the replicate names that we expect and the bioreplicate and condition values that are the ones that Mina gave me. And in this case, it's just, a set of concentrations, right? This is what we want to do is we want to identify the peptides that are changing, and they're the ones that were spiked in at various concentrations. So each concentration point we're going to treat as a different condition. And then Mina's going to show us how to run the statistics to do comparisons against that condition. So just go ahead and select those. Don't select the header row, but select the body of those annotations, bioreplicate and condition, and copy. So get the marching ants going around the S1 through S8. And then if we switch back to Skyline, is there anybody who still needs time to get Skyline? Do you need time? You're still loading the file? Okay. All right. Well, so for the rest of us, we're gonna where we'd like to be is then to open up the document grid and switch. So we have our transition counts here. Everybody looking at transition counts? We want to switch to the replicates view. Wow. Oh, yeah. And then, well, okay. So I guess if you're loading, you can't do this. Okay, so we'll wait. And now you can see that you have the sample dilution factor. A lot of people were like, where's the sample dilution factor, right? So the Skyline Daily has sample dilution factor and other, and the Skyline 4.1 does not. So it's a new feature. Anybody, you still need more time? How? Okay, so you got a slow computer. Yeah. If you don't have 16 gigabytes of RAM, this is gonna get really painful quick. Uh, so, so look on with somebody else. Okay, so we're missing the annotations we want, and that's because we have to go to settings, document settings, and check them, right? They're there because we opened that file. So go to annotations and check them. And you might, if you want to be friendly, you might also go and check MS Stats Input Plus. We decided, or at a meeting, we decided was what would you want to have your reviewers have if you were processing your data. In my case, I was considering with Skyline, and I said, oh, the Skyline document and the reports you used. And that's when I realized, oh, we should just make it possible to include those reports in the Skyline document. So the answer becomes, just give me the Skyline document and I should have everything. So if you're going to publish, I highly recommend that if you exported some reports out of Skyline, that you include those in your document settings so that people, you know, along with your annotations and everything, so that it makes it easier for people to reproduce what you did. So click OK. And once you do, then if you had the document grid open, you should see bioreplicate and condition appear. Everybody got that? And then if you put your cursor or you put your selection in this bioreplicate top upper left corner of the annotations. And again, this is where you want to make sure that it's not a blinking cursor, but a full blue box that covers the whole rectangle. And then you can just Control V to paste, and that will paste in all those annotations, right? And then you can kind of double check. Yeah, this is sample 8, and all the way up to sample 1. That all looks good too. So, yeah, okay. So if condition isn't a text value for you, I think that's just because you didn't open up the other document, or I don't know what. But if it's not, you can just go to condition. You can go here, edit list, and then choose condition and edit it. And then you just want to change it to a text type instead of a value type. So then if you change it to a text type, then you should be able to do that. You're saying it's not in the same order? Why not? What's the order? Oh, okay, yeah. So then again, you can do everything in edit list. So if they're in the wrong order, you just change the order, right? Using the up and down, right? And then click OK. But in this case, it doesn't matter because we're putting the same value in bioreplicate and condition. So all you need to do is get your condition to be free text and then paste into it. So does everybody have that? All right, so then the next thing we're going to do is then the final thing that we would do to prepare for running some statistics. So this is going to be discovery level statistics, right? We haven't done a whole lot to actually, you know, to try to have. Well, we haven't done any refinement. We've just taken every peptide that we could detect in DDA, and so it's similar to label-free proteomics. For those of us used to doing targeted proteomics, we would definitely do some level of refinement. And I'll show you a quick slide on that in a moment. So yeah, we tend to think that just measuring everything blindly is going to lead to very noisy measurements. But you know that you can hope that your statistics will sort of tease through that and find something useful. But the wider you cast your net, the less sensitive you're going to be, right? So if you really want to measure something specific, it's not a good idea to go at it this way, right? If you can narrow down what you want to measure, you can get much more higher precision measurements by spending some time on refining your assay. So, but anyway, so but we at this point we can run statistics. We can use statistics to do just a very broad like discovery thing, and then we can follow up with validation experiments to try to get more precise on what we think we see. And maybe we have a high default discovery rate in this first phase, but maybe we fix that by doing some PRM or SRM after this. So let's go to file export. Oh, this is import, file, export. And you can see that actually one of my export choices and my import choices are annotations. That's what was added recently. And I'm hopeful that that will allow us to just, rather than pasting those annotations in, it'll allow us to import those annotations. And it'll allow us to import them from the command line so that we don't have to do a manual step here. So, but right now we're going to export a report. And we're going to choose that MS stats input plus, and we're going to use invariant. So invariant format, the thing about the main thing about invariant format that makes it a little bit easier for R is that it makes all the column headers, it takes the spaces out of them, and it also makes them all English. So if you were running the Chinese or Japanese version, if you just export a report in your, it will be your, it won't show you US English, it will show you, Japanese, and then you'd have to use Japanese characters in your variable names inside R. So it's typically, if you're going to use something for R, you want invariant format. And in fact, when we use MSStats as an external tool, we always export invariant format. Invariant format will also use a US English US decimal point. So if you're from Europe, you're used to a comma, but so it just normalizes everything to a very expected format that is good for working within R. So I guess we could start this. It's pretty easy to cancel. Yeah. Yeah, you missed it. You missed when I said open that file. So there was a file, because all of your issues point to missing the opening annotations.sky. But don't do it now. Just go ahead and export MS stats. You don't need the plus. You have it. So wow, that's interesting. Okay. Anyway. Okay, you installed MS Stats. Okay, so anyway, so that's good. So yeah, just use MS Stats. I did not have everybody install MS Stats and you would have to install MS Stats specifically into this daily version, if that's what you're using. So, but anyway, for the rest of us, we can go ahead and click import. If your machine, and then we'll. I'm going to stick it in pub brooder and msstats input. I'll call it msstats input dash brooder. And then save. And Skyline needs to build the report, and this, and even on this machine, I probably have a lot open right now. I think this is going to stress Skyline's memory and the processor speed here. So this has taken me minutes on to do, and so we may just cancel out of this. It's fairly easy to cancel. But this is how you could go away and have a coffee and and come back, and this report would be exported. And again, if you have a fast desktop, this will be nothing. And then you also have, well, I guess you can export reports with command line. So there are lots of options for getting this more quickly. Yeah. So now my instance of Skyline is starting to like switch windows and stuff, which means that it's getting really close to the memory limits. And I might do things like shut down Chrome. But yeah, this ends up being a big report because MS Stats as a statistical tool, it actually exports peak areas for every transition, where we tend to frequently we'll just use a summary value for every peptide, so a total area for every peptide, but MS Stats likes to have a value for every transition. And it's been explained to me by Mina and Olga that they think that we can do better statistics off of that, because if we have 6 transitions, some of them may be nearing their limits of detection, and the regression statistics that they're using can compensate for that somewhat. So anyway, I'm just going to cancel out of this because we had the report. I guess you could too. I guess that's sort of the end of what we're going to do with Bruder until we get to the statistics. So I will we can wait and we'll see if anybody manages to finish while I introduce the CelebSec dataset, which actually even gets a little bit larger than Bruder in some cases. So if we go to our USB DIA pub, there's CelebSec 2015. I'm going to open Chrome back up again because I think I had the paper in here. Yeah, so reproducible and consistent quantification of Saccharomyces cerevisiae. Yeah, because this is really trying to use just everything on my machine right now, I'm going to go ahead and cancel my report export. Which would be better done at a time when I don't have to do anything else. I will, however, save my document, which is going to also take some time. But I think I can get. So this is the experiment, and it's sort of I would say a first experiment from the aerosol lab dealing with the idea of a pan-organism library. So they tried really hard to build a library that would, cover not just, they did fractionation. Actually, I can show you quickly. So they did a bunch of DDA. They didn't just run some DDA runs on their samples and then use them to build the library. So they didn't just run on the samples of interest. They went to, let me see, I think I can show this to you. All right, so here's my full, and this is all on the flash drive too, I just realized. So this is the DDA data. Here you can see that everything got converted to MZXML, and then they searched it against this FASTA file, which is a standard yeast FASTA file, and then this is the iProfit combined results. So they used peptide profit. I can't remember what the search was done with, but it's in the paper. And then here also are the raw WIF files that we could use to extract chromatograms from. So I did a fair amount of work just with the DDA data, importing it, extracting chromatograms from the MS1, looking at it, and getting a sense for the raw DDA data that they built their library out of. I think I may have used it to get more precise IRTs. So there are 2 ways that you can build your IRT library. You can just kind of point at it and let Skyline get the IRTs out of the spectra. But there's so who can tell me an issue with IRTs from spectra? Well, for one thing, I showed you that DIA data where we had a spectrum on either side of the peak, right? And so when we have a retention time, we like it to be the retention time of the peak apex. And in that case, it's probably going to be fine because we'll average the two and we'll get something close to the peak apex. But if we're consistently picking, you know, if spectra are consistently getting measured on the early end of the apex, then our times might be early. So our time, you know, we would prefer our time, and then I actually skip this as, yeah. So here is the big issue, right? That sometimes I get IDs like, you know, I don't know, somehow some of this peptide, and this is one of the IRT peptides, eluted out here. And then you can see that there's this, you know, you can see the light lines are where it was identified in other runs. But you can see that now there's also some tailing going, you know, there's some, and I think that this sort of thing happens even worse. Well, you can see the peak tails. And so that happens even worse if you over inject the IRT. So you really need to be careful. Like, I don't know, Ben said, oh, nothing can go wrong if you use IRTs. And I'm like, oh man, I don't know about that. I don't know about that. I've seen plenty go wrong with IRTs. So, and one of them is injecting too much of the IRTs. And that actually, in one sample I saw, it caused the IRTs to have, I mean, this is what Bruker told me, oh, yeah, we injected too much of the IRTs, and that's causing more variance in the mass accuracy. So I guess when they get, you know, saturated, they and the mass accuracy also goes off a little bit. And so I had to use a wider extraction window because otherwise I would see signal dropout in my chromatograms, and Skyline was having a hard time picking those. So yeah, and then obviously if you do that in DDA data, then you can get spectra like measured way out at the end of the gradient for your peptide. So I did do some work. Originally, I just took the mean average of all the IDs, which you could pretty quickly realize would put me somewhere like here. You know, or maybe I guess there are more over here. It would put me here, but that has no relation to the peak. So now we use the median, and actually even to get really accurate, because you know diagnosis IRTs are used a fair amount, and they have a number of peptides that are prone to tailing. There are certain peptides where I use the 30th percentile because I know there's like two or three peptides in the diagnosis IRTs that are prone to tailing, and so if I'm doing spectra, I'll pick an earlier, you know, I won't pick the median because the median is 50th percentile, and that might end up being somewhere out here. And so I'll pick like 30th percentile on those specific peptides. But I couldn't do that for every IRT standard, and I certainly couldn't do it for endogenous. So it's way more accurate to get this peak apex, right? That's going to be that's the closest to what you want for all chromatogram extraction. So it's very useful to have this DDA data, and I've got it all, and I've built a library out of it for the CelebSec data. So if we go back to, if we look here on Samsung, this is my big flash drive where I have all the data that I could give anybody. Here's the DDA runs, and there's the iProfit combined, and you could build a library just as we've been building a library from, I guess Skyline is still working on the MaxQuant library for Bruderer that we started this morning. People who were here early this morning, we started a library, and it's taking quite a long time to filter down to the non-redundant library, but we're almost done there. And then the one other thing I wanted to show, here are the, whoops, that's not it. Here are the files. So the people who did the CelebSec paper put a bunch of files up on up on a repository, but then I had to do some extra work to get some information about what they actually were. And then so this is my key for what they are. There are 3 different osmotic shock replicates, and they are these. And then this is the DDA, and you can see that the DDA, they did on-gel electrophoresis, and they actually did an osmotic shock experiment. So we were talking about, like, should you pool? In this case, they fractionated for their library, at least, right? So that we talked about, I mean, you could do all these different osmotic shock states. We got T0, T15, T30, T60, T90, and T120, which are probably the states that we want to measure in this experiment. And if we pooled them, then we would be diluting, some of the things that are abundant in certain conditions. And so in this case, they wanted a library, of a lot of things, and so they did all this fractionation, and this can be considered sort of a pan-yeast library, covering, everything they think they might be interested in measuring. Another thing that they did was, and Mike mentioned that they'd done some measurements against a standard that was the same standard that we'd used, so we were able to do the calibration to the copies per cell, and he showed the correlation graphs of that. Another thing that I found that they did was they did replicate measurements. So before they did their actual experiment, they built their whole library out of DDA, and then they just went and did DIA measurements, eight runs that they expected to be the same. So we're gonna look at that for sure, because that gives us the ability to do a little bit of refinement. So they're currently in the field, there's some tension between, measure absolutely everything and then let the statistics work it out, versus do refinement and measure a smaller set of things that are more likely to give you high precision results that, we think are going to do a better job with the statistics. So that this CelebSec data set, because of the way it was, because of what they did, has been fairly rich in terms of its ability to be reanalyzed. So let's go start working on creating a file for it. So if we go back here to the Bruder data set, we can go, so we want to be in this Skyline daily version, and we can just go new. So we're going to create a new file for the CelebSec data set. We'll even just go start with settings default. Oops, I didn't want to do that. Settings, default, and no, I don't want to save my settings. All right, so then the first thing I would recommend to do, so we're now engaged in okay, we're going to create a set of coordinates to measure the CelebSec data. And here there is an assay library. In this case, I thought the assay library had enough problems that I didn't even want to use it. I think it was allowing more neutral losses, and there were cases where there were just 2 transitions per peptide, and so I decided, okay, I'm going to go back and settings default. Yeah, just go with settings default. Okay, yeah, so all I did was click new and settings default. So I just start with a blank document. And the first thing I'm going to do is I'm going to turn on integrate all. So on all these DIA experiments, we just turn on integrate all, because we're not going to do any further transition refinement. We're not going to be picking special transitions or anything. And then we're going to go to peptide settings. And the first thing we'll do is we'll go to the digestion tab, and allow for 2 miscleavages. So this again is 2 miscleavages if we saw 2 miscleavages in the DDA data. So we're not just generally allowing for 2 miscleavages, we're only going to do it if we saw it in the DDA data. And we're gonna, yeah, that's good, thanks. And we're gonna add a background proteome because I've already created one. Oh, we're gonna add the yeast forward and reversed and open, and we'll go to the Celebsec folder, and there's a pre-created yeast Celebsec yeast forward and reverse proteome database. Does everybody at this point understand how I got that? Right? So in fact, in this folder, I think there should be a SGD. So this is 03 Feb 2011. So that was the SGD. So you can go up and get an SGD database off the web yourself. But the paper said that and it actually took me, I had to eventually get Ludovic Gillet to send this to me because it wasn't part of the file set. I was able to get the February 3rd, 2011 yeast SGD FASTA off the web eventually, but I was not able to get the forward and reversed. So I wanted exactly their FASTA file, so eventually I had to ask for it. So but yeah, so you could build this background proteome yourself from that data. And most of you have built at least one background proteome, right? Anybody who hasn't built a background proteome? Okay. So we're just going to open this one, and Skyline will read it and tell us that there are 13,263, which is odd because it should be an even number, right? I don't know. Okay. There was something that didn't get reversed. What? What do you mean? Is that the header? Yeah, so that's how we know what's a protein. But yeah, if you look at the FASTA file, which we can do just quickly, it's got interleaved forward and reverse. So it's got YAL01C, and then it's got reverse YAL01C, and it should. My expectation would be that if I went Control F and looked for this up arrow greater than with a regular expression, and then I did a count, it would tell me, yeah, there's an even number. So 13,434. And but there are going to be some duplicates, so I don't know. But I still don't know why. It still doesn't make sense to. But it's not a problem. Anyway, let's keep going. Click OK. Got yeast FR. And the next prediction, we don't really. Oh yeah, prediction. We're gonna add a calculator. And again, this is a calculator that I built. I gave this calculator some extra work that I can't really go into here, but this again, you could build a calculator right from the spectral search results, but I spent some time with the DDA data and built the calculator based on peak apexes, hoping that it would provide me better retention time prediction. So we can look at my models. In the end, have really good retention time prediction, retention time becomes the most important score by far. But I'm not sure I managed to do that with this. It's definitely the retention time definitely shows up as a more important score than in the Bruderer data. I think. I don't know. Okay, so click open, and we're going to click So you want to click on this. We're in peptide settings prediction. You want to click on this calculator and add a calculator, and we're going to open one. So we opened a Proteome DB that I built. We're just going to open a bunch of things that I've already pre-built. But hopefully you know how to build them yourselves at this point. And we need to go up to the CelebSec folder, and then you can see that there's a CelebSec yeast recreate 02A. And the 02 means that I use 0.02 as the cutoff score. And then that's actually in the paper. The paper says that they did an analysis and found that they could get a 1% false discovery rate with a cutoff score of 0.02, which that's a posterior error probability, and that means that the likelihood of any spectrum match that has a posterior error probability of 0.02, you take 100 of those, 98 of those are going to be false discoveries. That's what the statistics are telling you. And I was like, why would you do that? But I went ahead and did it at the level of IRTs, because okay, so I have some extra IRTs for things that are junk, but I'm not going to include them in my query set. But I think even if your statistical tools tell you that you can have a 1% false discovery rate by taking things with a posterior error probability of 0.02, you don't want to do that, because that's basically, you're just filling up your, you've reached a point where you're taking only false discoveries just to get up to 1%. So it means that actually your tools did a really nice separation, and you could stop much earlier, but you're continuing to 1% false discovery rate by taking mostly junk. So I went with that. I looked at that. I think that's just my end result feeling was that was yet another attempt to like have large numbers, and that I think trips us up sometimes. So but anyway, so that's why it's 0.02. It's 02 here. This IRT library actually has a lot more peptides than we're going to look at, and we'll see that in a second. So it's got 82,500 peptides, right, in yeast, and so that, that's certainly, if we, I think actually I might have also allowed. They allowed unconstrained cleavage. They allowed semi-tryptic peptides too, which gets you like another 20% more things. But we're gonna limit ourselves a little bit in this experiment. We're gonna use normal tryptic cleavage. So this is our I don't know, yeast 02 IRT calculator. So this has a lot more peptides than we're actually going to look at, but it doesn't matter. It's just, the ones we end up looking at, we're going to have a high degree of confidence in. You can see that it's telling us that the standard in this IRT-DB is the diagnosis standard. And click OK. And we'll just go ahead and set the time window to 10, even though we're not going to end up using that time window. And then let's switch to filter. And now this filter matters. It's going to decide what kind of peptides we actually add to our target list. And we're going to use 7 to 45. I think that's an exclude 0. And this will be somewhat similar to what the paper allowed. And for our library, yes. Oh, yeah, because there's a signal peptide that actually gets cleaved off. So a lot of these FASTA sequences actually include peptides that are never going to appear in the sample. And interestingly, our tools seem to find them. So like, yeah, our search results find them. So yeah, you'll get more peptides if you do this, but I think Mike would contest that they're not really peptides. They're not. They're probably all false discoveries. Do you have any? Oh, okay, okay. Well, anyway, okay. So then yeah, then maybe setting it to 0 is a good idea. But that that was basically what the lab was doing universally when I arrived, and actually the thermo pinpoint tool had that, and so I went ahead and made the default 25. But you're welcome to change it to 0. Uh, Okay, so we need a library for this too. So we're just gonna, so I'm gonna promise you that those of you who showed up earlier this morning, we started building a library out of MaxQuant results. I have shown you that in this SelevSec DDA, there is this, so I built a library using this iProfit PEP XML. So iProfit combined PEP XML, which is a library of all these DDA runs, right? So we have off-gel electrophoresis, and we have osmotic shock runs. So a bunch of fractionation to try to really get at all the peptides that we think might be relevant to our experiment. And yeah, so we did fractionation and varying sample preparations. So let's go. Well, everybody knows how to build a library here, right? So this is just one that I built. It's too big for me to give you all the files to have you, and too long to build for you to build it yourself. So we'll just click add and browse. And here you can see this. And this one says SelevSec yeast rebuilt 90. And again, that's the cutoff. So I used a 0.9 cutoff, which I guess leads to a less than 1% false discovery rate. But I still don't really want to, I don't want to take peptides beyond where 1 in every 10 is a false discovery. So we'll click open. And then we've got to give that a name, and we'll call that yeast SelevSec. And this doesn't really matter. It's not this library doesn't have any explicit peak bounds, but we're going to turn off use explicit peak bounds, which is something we just added for tool, so that we can build libraries out of information from tools like Encyclopedia, our own tool, and OpenSwath. Yes. Did somebody have a question? Okay. So I opened the library file in yeast SelevSec. So, not the redundant one. So there's rebuilt 90 and rebuilt redundant blib. And actually, I think if you tried to open the redundant one, Skyline will give you an error. So you want the non-redundant one. Yeast rebuilt 90. Under DIA pub SelevSec 2015. Okay. So then okay that. And then I named it yeast SelevSec, so okay. And then okay again. And then just check that checkbox, and we're going to pick peptides matching the library. So that's all good. And let's go to modifications. And we should, from the Bruder data set, we have some modifications. We just want to check oxidation M. What do people think about including oxidation M in a quantitative experiment? I kind of wonder about it because it's essentially a degradation, right? And we did a set. We had one of our rotation students do an experiment on degrading peptides, and we found that the methionine oxidation and an N-terminal glutamine, which I guess is prone to cyclization. Yeah. How do you say that word? Cyclization. So methionine and N-terminal glutamine were the peptides most prone to degradation. So I would say probably don't include them because degradation, right? In the best. So we know that some peptides degrade, and in the best you can hope for a degrading peptide is that you randomize well and it just becomes noise in your experiment, right? So some of your runs might have half the peptide that other runs, or even we've seen ones that degrade through the collection 200-fold. And so you've just included this thing that's going away 200-fold during your experiment. If you're lucky, you randomized and that just becomes this random noise when you're trying to quantify your protein. If you're unlucky, it can become a confounding factor because if you actually measured a block of healthy and then a block of diseased, the degrading peptide is going to look like, wow, it's way lower in the disease than it was in healthy, and it's just an artifact of degradation. So I actually kind of think including oxidized methionine in one of these experiments, I'm not sure I would do it. And might even come up with a way of excluding N-terminal glutamine from what we've been talking about. But we'll continue going here.
Peptide that's not modified, but could be modified by a methionine oxidation.
Yeah.
You could actually, you're only looking at the MS2 signals, you want the precursor signals, and that can look like, the oxidized one can look like the unmodified one.
Mm-hmm.
So sometimes we throw in the modified stuff just to be able to detect them, and then we'll kick them out later for
okay.
processing. I mean, that's one.
Yeah. So, and in fact, we're right now we're creating just a sort of broad document, and we're going to go through two different ways of processing it. One is we can process everything and then hand it off to Mina and have her tell us what's changing. And then the other one is because we have replicate data, we can actually look at what do we think we can measure precisely, and that we just say, okay, we did 8 replicates. What can we get a CV under 20% on? And we're just gonna try that as a filter. So that's where we're headed. Let's click OK. We're done with peptide settings, I think. Is everybody caught up? Okay. So now it tells us, hey, you said you wanted IRT standards, and they're not in your document yet. Do you want Skyline to add them? And if you do, we can add a certain number of transitions per peptide. And before, for the Bruder data set, we imported this special assay library. In this case, we're not going to use that. But we'll click yes to 3 transitions per peptide, and we should end up with something that's a lot like what we got into the Bruder data set last time. So those are our diagnosis standards. And now we're going to go on to transition settings. Did everybody's got integrate all, right? Yeah, okay. So let's go to transition settings. And we'll start with full scan. Since we're doing a full scan experiment, we're going to skip over MS1 because we're not using MS1 in any of these things because it's just going to make everything larger and we're trying to do things on a laptop. And we're going to do DI acquisition. In this case, we're doing TOF extraction since this is triple TOF data, and we're using 18,000 resolving power, and, you know, probably high selectivity extraction. And then now we need to do our isolation scheme, which actually might be the swath 25MZ. Let's just select that and then have a look at it. And it's not quite the swath 25MZ. Yeah, so this is the current swath 25MZ, which I think is, you know, pretty good. You can see that actually, well, I don't know. Anyway, so that's not quite what was used in the CelebSec, so cancel out of there. And now what I'd really love to do, we'll go ahead and add, we're going to add one. And what I'd really love to do is, it's going to be pre-specified windows. I would love to be able to import it, but I forgot to put a WIF file on all of your drives. So we're going to calculate it, which runs the risk of getting things wrong, but I think I figured out the right way to do this morning. So we're going to go from 399 to 1200, and we're going to use 26MZ measurement windows with a margin of 0.5. So I believe, yeah, and then we got 32 windows. That's a typical sort of original style swath assay. And we're not optimizing window placement because we got the margin. Does everybody have those settings? So click OK. And now the one thing that changes here is that they actually started at 400. So this first window is actually 25MZ measurement, and then every window after it is 26MZ measurement. So, and you can see we end right at 2000. So, and then we can graph that, and we can see this nice graph, and, you know, feel confident that, okay, yeah, this was what happened. It's got margins, it's got 25MZ measurement windows, or 26MZ measurement windows, and 25MZ extraction windows. So we'll call that I don't know, CelebSec swath. Yeah, I had to do, you know, I mean, you could leave it 39, but and then you would, yeah, but then you would get peptides that are in that range that, you know, well, you'd get peptides that weren't even measured, because that would allow 39.9.5, and we would start, so you would get some peptides that were between the actual measurement, or started at 400. Our extraction we'd like to have start at 400.5, and we would get things between 399.5 and 400.5 that we'd be extracting. Some of them wouldn't even be present, so we would get garbage, and some of them would be in our drop-off range, right? So anyway, so this is what Skyline would give you if I had put a WIF file, and I probably didn't even have room to put a WIF file on. If I had put a WIF file on and we'd done import, you would have gotten exactly what we have here now. So, but definitely if you have existing data, my favorite way of getting things now is to use the import, because then you're sure that you're matched up with what the person measured. Okay, so, and then we're not going to use MS IDs. We're going to use retention time prediction. And we're going to go ahead and stay with the default of 5-minute windows, or five minutes on. That gives us 10-minute windows, 5 minutes on either end. And then now we want to go to instrument. And I think we can be fine with, say, 300 to 2000. And that again is limiting our fragment ions. but not limiting our but our precursors are limited by the isolation scheme to 400 to 1200. So this is a wider limit than our precursors are more limited than our fragment ions. And now if we go back to the library, let's go to filter first. And in the filter, we're going to say 2, 3, and 4. And charge 1 and 2 fragment ions, and then Y and B. So those are 2, 3, 4 precursors, 1, 2 fragments, and then Y and B fragments. And then we want to say ion 3 through the last ion. So we're not going to have any Y1s, Y2s, B1s, or B2s. They're really not very selective, and swath already. I mean, we don't even exclude them. We don't even include them in SRM, but swath DIA is even less selective, and so I would say there's going to be a lot of stuff there, and the Aerosol lab also makes that impossible, and it looks like Biognosis as well, by using either 300 or 350 for their minimum MZ. They're not going to get any 1s or 2s in that range either. So, all right. So, yeah. So now we go to library, and because this is these are high-res spectra that were used in the library. And high accuracy, we're going to use basically a 50 ppm mass tolerance for picking our fragment ions. And then we're going to go with 6 and 6, just like the Aerosol lab recommends. And then we're going to go with filtered product ions. So if you leave this button, if you leave this radio button at the top, then it's going to use Y1s and Y2s. So you have to choose filtered product ions to actually have this exclusion work. That means that you must not have chosen ion 3 to last ion. Weird. Okay. Unusual. Okay, so that's terrible. Okay. Hate it when that's the answer. All right. So does everybody have that now? Got the settings? Okay, so let's get to work on let's get to work on actually getting some targets. So this is just we've set all our settings and we've got the IRTs in here. The next thing we want to do is file, import FASTA. Oh, yeah. So one thing, so actually you don't have to follow me here, but in the digestion tab, we've chosen triptych digestion. The Selevsek experiment, if we wanted to more closely imitate the Selevsek experiment, I created this semi-triptych digestion and that's what they did, and you'll get like an extra 20% more targets to consider. I just am not sure that, certainly we're pressed enough for memory at this point with what we're doing, so I'm not going to include the semi-triptych ones, and we typically wouldn't, but Ludovic Gillet swears that we should and that there's useful information in them. So anyway, just wanted to point that out. And so yeah, if you see that, if you go back to the manuscript and you're like, wow, why are our numbers so much smaller? It's because we're not. One of the big reasons is because we're not using semi-triptych cleavage. And the search results include a fair number of semi-tryptic peptides that were found with high confidence. So import FASTA. And then we need to find this forward and reverse FASTA. So in the CelebSec folder, we should have SGD 03 Feb 2011 forward and reverse FASTA. And just open that. Everybody got that? Okay, open that. And Skyline will start processing it. And that may take a few seconds. Anybody have any questions at this point? While we're waiting? Yeah, well, so in this case, we're actually adding targets to our we're adding targets to our document, which actually we're doing the entire proteome. But what we add to our document could be a very small subset of the background proteome. So the background proteome is supposed to represent what's in the sample, and yeah. Yeah, probably you wouldn't do that, right? Like it was Swiss Pro, you mean all organisms? Like, oh, I made it. No, it's supposed to be your sample. So it could be all of human, and then so yeah, you'd have a set of proteins. So yeah, it's like you did some sample prep. Okay, what's in your sample? Maybe you did a nuclear prep. Okay, I only want a FASTA file that's proteins found in the human nucleus, and then so the background proteome, in this case, we end up with a background proteome that is exactly the same as what we're importing, but that's just because we're doing the experiment, which is the discovery experiment. I want to try everything, and that's kind of as wide as we can go. We're not even quite that wide because we're using the spectra. So you'll see, yeah, okay. So I'm not totally that wide because in the end, Skyline imported the FASTA file and said, well, your spectral library tells me that these things are not in your sample. So it's throwing away, although these are both forward and reverse. So it's basically throwing away 4,500 proteins. And there's probably about 6,500. So we're really only going to measure 2,000. Well, yeah, no, that's not right. But anyway, so let's okay this. So this is saying, yeah, we're going to discard a bunch of proteins for which you had no matching peptides, and click OK. And now we have 4,400 proteins. Right. So yeah, we end up. You can't just divide in half because most of these proteins are not reversed. So yeah, we're going to end up with around 4,000 proteins when all is said and done. So now you can see that there are these reverse things sort of sprinkled in, and so this is where I want to go to edit, refine, sort proteins by name, and that has the nice impact of putting all these reverse ones at the top or almost at the top. There are a few things that have smaller names, but you can see here they all are. Let's go ahead and take these other proteins that are not reversed, and I select the top one, hold down the shift key, and then down arrow to multiple select them. Everybody got that? And then you can click these scissors to cut them out of the document. And then now we can go page down, page down, page down, and then so 3 page downs, select the top non-reverse thing, and then click this clipboard to paste them. Taking a second to work that out. So okay, so now we have our IRTs, and then we have all the reverse peptides above the non-reverse peptides, and we can do back of the envelope false discovery rate right here. So what's our protein false discovery rate? So you'll notice that I'm selecting this top Q045 protein. What protein is that? That's a protein 118 in my document, right? So you can see that, right? So right here, 118 out of 4,485. So I can back of the envelope false discovery rate. I can just go down here, Windows 10, and say 118 divided by 4, yeah, it's going to be 5%. 86, and well, it's not quite 5. It's more like 2%, 2.5%. So yeah, it's higher than 1% false discovery rate, but there are things that we are now going to do to improve this. One of which is we're going to go ahead and we're going to do a quick refinement. So go to Refine Advanced, and we're going to say remove duplicate peptides, and then minimum one peptide per protein, which will get rid of all proteins that are, have a duplicate. And click OK. Repeated peptides will just basically keep all peptides in the document, and it will just remove the second instance or third instance. It will keep the first instance of the peptide. So if you don't want to lose any peptides, you want to measure all possible peptides, you would choose repeated peptides. If you want to have peptides that are specific to your proteins, then you would use duplicate peptides. So and that's what we want. We just if it appears in multiple proteins, we're not going to measure it. Yes. Okay, that's true. Okay, well, so we don't solve that problem for you. But if you want to post it to the support board, we can think about it. Okay, so let's click OK. And that actually, so that removed some proteins. It moved like 200 proteins. And actually, I can go back and forth with undo and see that well, don't everybody do that, because apparently undoing it takes longer than doing it. But eventually I see that, okay, I've got 350,000 transitions, and then when I redo it, I end up with 300,000 transitions. So I'm losing quite a lot of transitions. And now you can see that I'm on protein 106. So I don't know, my false discovery rate by protein stays about 2.5%, but by peptide, what's my false discovery rate by peptide? Anybody? False discovery rate by peptide? Yeah, much less, which tells me something, right? If all my false discovery rates are piling up, sort of like has been explained here, they're all piling up on one-hit proteins. So another thing I could do, not everybody has to follow this, but you can go Refine, Advanced, and we could make the minimum peptides per protein 2. And then we would find that we have only one reverse protein that got more than one, but we also lose, another 500 proteins. And the question is, do we care? And maybe Mina can help us with that, it's a question that she and I have been investigating. My sense is that single hit proteins, while being much more likely to be false discoveries in themselves, they also appear to be more likely to produce false discoveries quantitatively. So if you require multiple peptides to be covarying in order to show that a protein is different, then single hit peptides only need to have one peptide that is changing. And so it's a little bit, they're more likely to be false discoveries, proven by the fact that all of them go away essentially when all of our proteins go away when we demand that we have multiple hits. And so now we have a false discovery rate of essentially nil. But they're also more likely to create false discoveries quantitatively. But I'm going to undo that. That's not what I did for this experiment, but it's something worth considering for sure. And you can see that it only changes the number of transitions by about 2,000. So the number of transitions represented here and the number of measurements represented here is very low. So okay, so this is our document that we would now go process, and you can save it. And I will save it to hands-on SelevSec. All right, and that's it. We're going to have a break, and then we'll come back and actually look at the SelevSec data and how we process it and what choices we made, and then eventually we'll get to doing the statistical analysis.